Hello, everyone. Thanks for joining this webinar. In this webinar, I will present the latest WinDriver version, 16.3.0 main features, fixes, and we will discuss IPC, which is inter-process communication, a special API we offer. My name is Daniel. I'm the Technical Customer Success Manager of WinDriver. This is my email. Feel free to send me messages, questions regarding this webinar, requests for other webinars. We have a lot to cover, so let's start. So what are we going to talk about today in the next hour? We will see the release notes of the latest version, and we'll talk about the importance of upgrading a version. One feature that we have that not a lot are familiar with and has a lot of potential in making the use of your driver, the driver you develop, easier for your customer is the NSIS installer. We will have a lot of demos in this webinar, so we can see a step-by-step how can we use and utilize WinDriver's functionalities. Everything I will do here in this webinar, you have on your computer with WinDriver. So you can try this yourself, whether live or after that, if you're seeing the recording. We will demonstrate how to create a self-extracting package, an executable file for installing on Windows. Then we will talk about IPC. We will see an overview. What is IPC? Why do we need it? Create groups, send message within the groups, allocating a shared buffer, and raising a shared interrupt. Everything again with a live demo and explanation on the code. So we released version 16.3 back in July 1st this year. It contains mostly fixes of the previous version, 16.2, which included significant improvements and features. We had 2 webinars for 16.2 features. They are available on YouTube. So if we talk about the new features on 16.3, we're talking about the option to generate static or dynamic libraries with CMake. So if you go, this is a screenshot from Linux, you can create a separate library for application logic. It's a .a file, it's the equivalent of a DLL file, where you can take only the logic of your driver and not the UI we offer and implement it on your driver, your application. We have console applications upgrades, the PCI DIAG, WD-REG, and the generated code with colorful output. We will see it also today during the demos, which makes the whole experience more pleasant and even easier to troubleshoot and debug. And the Linux installation will now feature a colored ASCII version. So if you're using Linux, you probably notice a huge WinDriver logo, which is nice. We added support for newer kernel versions up to 16.9.4. One thing that WinDriver, maybe one of its greatest benefits, is that it keeps update with the technology, with the latest kernel version, with the requirements, with the compliance. So we do the work for your driver to be able to run on the newer kernel versions, which we all know are more secured and more and faster, has better performance. So it is very important to upgrade your WinDriver version, and as a result, your driver. The way it is done, we have a section for it on our documentation. It is not supposed to be that hard. Simply generate a new code in the new version of WinDriver, let's say 16.3. Take out the unused code, from the generated code and gradually merge your current code into the new generated code. And then build it. If it builds and has no problem, this is great. So it goes smoothly. If you encounter issues, contact us. But we really encourage all of our clients to upgrade their versions because they include significant fixes and are updated with the latest kernel versions. If your driver will be based on an older version of WinDriver and your customer decides to upgrade the kernel version, the driver may break. So we recommend keeping up with the latest versions. We will have a dedicated webinar for upgrading your driver and WinDriver version. And we have fixes for DMA issue on Linux. If you're using ARM64 NVIDIA IGX, we created support for this platform, and we had the PDA flow graphic issues resolved. Okay, so let's start with the first subject in this webinar. Redistributing your driver-based package as a self-extracting exe. So in order to create this package, you need to download NSIS. It is free. You can download it from the internet. And basically what NSIS does, it is packs your driver as a user application, installs the user application and the renamed driver, and provides an uninstalled executable file. So if you had to done this by yourself manually, I will show now how simple and easy it is, and impressive also, to create such a package. So let's see how it is done. This is the code generation option. Another note, this is more of advanced content. If you are not familiar with WinDriver at all, you may have a lot of questions about what am I doing. But if you already used WinDriver or saw previous webinar, like the introduction webinar, then things should be more clear. If you have questions, send me an email. But this is a more advanced content, so I will not go through every step on what is WinDriver and what this functionality does. So if you're probably familiar with this window, it's the code generation window. After clicking generate code, you simply choose CMake makefile with NSIS installer generator, and we will do it shortly. And it will create the executable file. Few notes. This is the support is starting from WinDriver version 14.3. It requires Visual Studio 2019 and up, and make sure you install these dependencies, the C++ CMake tools for Windows, and the desktop development with C++ from the WDK. Make sure that the path environment variable includes the path to makesys.exe. Go to our documentation 15.2.3.2, and if you're not sure what I'm talking about, and we have a full explanation of what needs to be done in order to make this work flawlessly. Okay, so let's go to the first demo. Now, in this demo, I will start the demo by generating a new code. Okay. Let's go here. And again, I won't explain every step of the way, but we'll start with generating a code just to cover the whole process. So I'm starting a new project, and I'm choosing a device. I won't make any change to the device, so it really doesn't matter which, but let's call it NSIS demo. I don't want to install the INF, and I am able to access the device because I already have this INF installed. You're probably familiar with this window, with the configuration space and everything. I won't change anything because this is the host computer, and I don't want to change anything. Let's click Generate Code and choose CMake Makefile with NSIS installer generator. I can create a separate library, as I said earlier, DLL library. I don't want either of these. And let's open our folder. Okay, let's close WinDriver. Okay. Now that we have the folder here, let's open Visual Studio. Now, I'm going to use a CMake file. Okay. We want to open a CMake file. I want to say something about the CMake. CMake file is our go-to build tool. This is the best practice we recommend using. It is fast, it's easy, it is easier to troubleshoot, it is cross-platform. It is a great tool to build your application, even not on different environments, on every environment. So if you are not using CMake, I recommend start exploring it and transfer to it, because it is really easy to build your solution with it. So as you saw, I choose File, open my CMake file, and it says it is ready. No, it's not. Now it says it's ready. Okay, Visual Studio suggests, but you see what happened here? So I only opened the CMake and it already started to work on it and start to go through the CMake file and extract everything. So here I can go to a switch solution and go to CMake target view. And here I see all my files, all my files. Now there are two important files here. All of the files are important, of course. This is our code. This is the generated code. But for this demo, I want us to look first at the CMake lists. So we are going to build a self-extracting executable file. This is its details. Okay, so we called our project NSIS demo, and we have the language and we have the version. You can change and modify it as per your driver's name and version. Down below, you can see that you have different descriptions: the package vendor, the package version, the version, and other components. You have the uninstall commands and everything. Go through it, see exactly what it contains, but it is important to modify and edit it as per your driver and application name and version. Also, the description, the terms of agreement, and we will see shortly what it means. Everything is being added here. This is the package creation section. This is another major, an important file, the CMake settings.json. What we need to do here is to add a package to the build command args. So we have it here. We add the v-v package to the build command args. And all we need to do now is to build this driver. So I'm building it. Of course, I will get errors. Permission denied. This I haven't got. Okay, so Let's try to run it as admin. Again, let's open the CMake, NSIS demo. Let's give it a second to set up. Okay. Everything is out, everything is looking good. We build it, and as you can see here, we created a package. Okay, so build or successful or succeed. Let's see what we got from this package. I'm going to NSIS demo folder, out, build. Okay, here I have the application, but this is not what I want. I want, sorry, the installation. I'm going to the Redis folder. And if you already created a file with you're probably familiar with the redistribution folder. Okay. I don't know what's wrong here, but sorry. Let's build it again. Sorry for that. Live demo. Okay. Here we got the V package. Okay. Okay. Here we have it. We have the package, NSIS demo version 1, Windows 64 generated. It's on build x64 debug. Let's go and find it. My project, NSIS demo. And here we have it. So once we have this executable, we can start installing it. Let's see how it looks. Welcome to NSIS demo. This is the parameters from the CMake file setup. This is an installer. Okay, you can have the license, the agreement. Just this is what I said. You will need to have your terms of agreement here. You can edit via the CMake file, the list we saw on Visual Studio. I choose I agree. You can choose again the location. You know this this whole procedure. Click next, and I want to install the application. I want you to see it. I had a window opened with all the installation script, and then I click finish. So now I've done installing the NSIS demo application, the one I created. Now let's go to program files and see our folder and what it contains. NSIS demo. Okay, and you are probably familiar with this list of files. We have the INFs, we have the BAT files, the sys file, the catalog file, and everything. So this is basically your distribution package only extracted with the self-extractor, with the executable. Here we have the logic. And what we also have, in addition to the regular distribution package, is the option to uninstall this application or this folder. So let's click uninstall. We have it here. It was really quick, so completed NSIS demo and installation, and it is done. It happened automatically with the script in the background. Makes the life of you and your user easier when talking about the installation of your driver. There is a lot of things to a few more things to explore in the CMake file, but I recommend going over it and add your update, your details, your version, your license agreement, and create a nice and friendly self-extracting package. Let's go back to our presentation. Don't forget to add the -v package under build command args. Okay, let's talk about inter-process communication. This is the other API, the API we will discuss now. Let's talk generally about API types. WinDriver works in both user mode and kernel mode. The user mode API is called high-level API, and the low-level API is called, the kernel mode API is called low-level API. In the past, we offered only low-level API, and then we started to add high-level APIs that are equivalent. The high-level APIs are more sophisticated, easier to work with, and we keep updating them. So we recommend working only with high-level APIs and not with low-level APIs. They are easier to troubleshoot, to debug, to operate, or to code. So we recommend working with them. Another thing we need to pay attention is the function name. So we have WinDriver function starts with WD something. So WDC is for PCI, WDU is for USB, and WDS is for server API. Okay, for every other name, the function is a low-level API function. IPC is, as I said, inter-process communication. It allows several WinDriver-based user applications to send and receive user-defined messages. What are we trying to solve here? Okay, so you have a device and you have several processes or applications you want to access and read and write to the device. And we all know this is pretty complicated. You need to create access mechanisms. You need to make sure that there is no resource overlap. You need to make sure that one process or application is not writing on another's memory segments or performing operations, and to prevent collisions. So what we offer is inter-process communication that allows one process to connect to the device, and the other process to send messages to the device, get informed when an interrupt is raised, and we will see more implications of this API. But if you're creating a more complex systems and you need your device to perform for more than one application, we recommend working with IPC. Because again, programming a driver with multiple accesses for a device is a headache, and there are a lot of things that can go wrong. But once this is your architecture, or with other processes that are trying to access via one process, it can reduce the complexity of this of the architecture. I just want to add a note. IPC requires a special API. and WDS, which is the server, is also another API that is required in the demo I will present. So if you are interested in IPC and you already have a license, contact our sales team and ask for a quote, because not every license, the evaluation licenses have this feature already included, but other regular licenses does not have it automatically. It needs to be purchased in addition to your subscription. So the first thing, maybe the most basic thing IPC API offers is to divide or let's say create groups of the applications, and you can manage the communication in these groups. Okay, so we have a multicast, a message that is sent to all the processes that are registered with the same group ID, a subgroup. Okay, if you have a group and you have also a subgroup, so send only to the subgroup, and a unicast, that message that is sent to one specific process. Let's have a demo. This one, hope it will go smoother than the previous one. Okay, so this tool is PCI Diag. PCI Diag is WinDriver utility. Let's do it like this. It enables an instant access to your device with no need to do anything, no coding needed. Second, let's put it here, and another one here. Okay. This utility can be found in the utility folder or in the samples C folder. I'll enlarge the text so it can be clearer. And what we have here is 3 different applications that are running simultaneously. Now, I want to manage the IPC here. I want to register the process into subgroup 1. This is another application, and I want to manage IPC and register it also to group 1. And if I want to find current registered group processes, okay, okay, so I have 1 and I have 2. And I want to add another one. So manage IPC, register process to subgroup 1. Okay, I see that I have 2 processes in the current group, 1 and 2. Okay. Now let's send a message. Let's send a message between, let's send a multicast, send a message to all the processes in the current group. So enter the message ID. 1 and 2 are already captured. So let's say 1212 and the message. Okay, so I've sent this message 1212 and I set that brief as the data. And I can see in the other applications that are in this group ID that a message was received. Okay, 1212, that brief from process 1. Okay, it's essentially the same message saying that we got a notice. So if we're talking about the most basic operation of IPC, so this is it. Adding a process or application or process to the group and send a message to it. Unicast, I can, this was a multicast, I can send the unicast. We will see it on our code. And later we will create a shared interrupt and see what happens when we raise an interrupt. Okay, so this was one example of the group ID and sending a multicast. Again, you can do this yourself. Go to WinDriver's folder, samples, see PCI diag or utility PCI diag, open several applications. You don't need to code anything, and do exactly like I did and see that it works. Okay, now this is let's say this was pretty straightforward. Okay, the demo. What I want to go over is the functions. Now, not all the functions because it may be too much, but generally, what stands behind the simple operation, which can seem superficial, but a lot of things going behind it. So, what allowed us to create, to register the process in the group is WDS, the server API, IPC register. This is it's a signature. It is available on our documentation. We have the process name, the group ID, the subgroup ID, of course, the action. The action actually enumerates between the unicast and the multicast. Okay. But the more interesting or the most important one is this one, is the IPC message RX handler. So what this does, what this pfunc does, it's a user mode IPC message handler callback functions, which will be called when a message was received by WinDriver from a different process. So basically, this pfunc is what happens when this message is received. Okay, this is for you to configure, to code, to implement your logic. We will review the code, okay, later. But just remember, there is a lot of things you can add to this functionality in order to perform the way you want. And we also have the P data, which is the data for the user mode IPC message handler callback routine. We will overview the code later. Okay, so we saw a very basic operation of creating groups and sending a message within the group. Now we want to raise an interrupt. Okay, we know that raising an interrupt is an important feature when we're talking about PCI devices. And once we have a group that only one application is connected to the device, we want to be able to perform operations with the other applications that are not connected to the device that includes raising an interrupt. Okay, so what will happen is we will raise an interrupt using the application that is connected to the device, and we'll create a callback automatically. The interrupt will raise at the other applications, and we can write a callback and other functions. Let's say send a unicast to the process if we want to send something, to perform something with the device. So we talked about the IPC register. And then what we need to do is send a pointer to that function as an argument to WDS shared int enable. Okay. After we've done that, we need to disable the shared interrupt, and this is done using these two functions. Let's see a demo. Okay. Let's close everything because we can, and open a new PCI diag. Okay. Okay, so this is a virtual machine with a virtual device. It's called Edu. I don't know if you're familiar with it, but I have the option to raise and interrupt with this machine. So I want to find and open a PCI device. I'm entering the number. Okay, and I can see my device details. Again, if you already used WinDriver, this is pretty straightforward and familiar to you. I can see I have an interrupt here. You can see the interrupt type. And now let's raise an interrupt without doing anything, just raising an interrupt, not registering it to a group ID or send messages, just to see that raising the interrupt works. So before I raise the interrupt, I want to listen to the interrupt. So let's enable the device interrupt. We had a full webinar about how this works, WDC int enable. So if you're not familiar with it, I recommend watching it. So now we are listening to interrupts. And now comes the part where you need to be familiar with your device, what raises its interrupt. So for my device is writing to offset 60. So I want to write to my device, 5, write to active address space. I choose offset 60, choose 1, and I have an interrupt, okay, that was raised. This is the message printed, got interrupt number 1, got the message data, and everything seems fine. Okay, now let's create a group and register this application while the device is open to a group. Okay. Want to register it to subgroup 1. And now I want to add this application with no device open to my group. Okay, this one is not connected to my device. This application, I want to add it to group 1. Great. So I have 2 applications that are registered to subgroup 1. And now I want to raise an interrupt here in my application that is connected to the device and have a signal here that says an interrupt was raised. How can I do that? Let's enable a shared interrupt via IPC. Group ID 1, and I have it enabled. I need to enable the shared interrupt also here. Okay, now the whole group is open for receiving interrupt messages. Now I need to raise the interrupt. Write to inactive, enter offset, enter data, and here I have it. I have another interrupt I received, number 2. Receive an IPC message that one of the processes raised an interrupt, shared interrupt via IPC arrived. You can see both of the messages regarding the interrupt was raised. Okay, so this is how to manage shared interrupt when only one application or process are connected to the device, and you can add functionalities to it. Let's see what it means. Let's go back to the presentation. Okay. So here we have the WDS shared int enable. Function. Again, this is its signature. It is available on our documentation. this function includes the process name, the group ID, subgroup ID, the DW action, which we went over. And here, this is your place to enter the callback, the what happens after the interrupt is raised. Okay, just to, you know what, let's open the code, see how it looks. Let's open Visual Studio, beside the YAG. Again, all of this is available on your computer if you've downloaded WinDriver. So you can just open it, open the code, exactly like I'm doing right now, and see for yourself. Let's go to CMake target views, shared, and everything is here. WDS. Okay, so this is our function, WDS shared int enable, called when the sample pfunc the pfunc. Okay, this one. IPC shared interrupt message event callback. This will cause the shared interrupt to invoke both this callback and the callback pass to WDS IPC register. So as I said, we have different parameters here. The first one is process name string, the group ID. Default, everything is defined already above it, the subgroup ID, the action, which tells us if it's a unicast or a multicast, you can see here, as I said, and the callback. Now, the callback is the most interesting part because this is the pfunc. This is exactly what defines what will happen after the interrupt is raised. Okay. So in this case, the callback or the what happens after the interrupt is raised is simply printing the shared interrupt, VIPC arrived, the message ID, the message data, and that's it. But you can add functionality here, the callback. Whatever happens or needs to happen after interrupt is raised should be defined right here. So you have a lot of room to add functionalities, to add anything you want to to happen after the interrupt is raised. This is where it takes place. Okay, and this is the code. Again, available for everyone who downloaded WinDriver. Okay, another thing I want us to cover when talking about IPC is the buffer sharing between multiple processes. So, as I said, one of the processes is connected to the device and transfers data, and it can be allocated during a DMA session or just a simple kernel buffer. So the first thing that needs to happen is to allocate a buffer, DMA or kernel buffer. This is process one. Then we need to get the global handle, okay, to retrieve the global handle of the buffer. This is also process one is doing using WDS shared buff get global handle. It needs to share the global handle, okay, using a unicast, a subgroup, or multicast. We saw how these messages are sent. And then the other process is receiving the handle and is able to access the device, okay, and the data, the buffer, and everything. So you can do it with the device itself, but you can also, I will demonstrate it with the memory, okay? How can we share this buffer, not to a device, but to a memory section. Okay, so let's open. Let's start from scratch. 1 and 2. Okay. I want to manage IPC. Add to subgroup 1, manage IPC. Okay, both of the applications or processes are registered to the same group. Now I want to choose number 10, allocate a shared kernel buffer with all processes in current group. Okay, so here I go, choose the size, say 5,000. And as you can see, successful kernel buffer allocation, I got the user address. The size is predefined in the code, so we will see that. But also, the other application or process received the handle, and they have the addresses, the kernel address and the user address, and they are able to access this buffer. So again, it can be done using a regular kernel buffer or using while using a DMA. Now, if you think of it, DMA or programming a DMA with more than one application can be quite a headache. Think that one process is performing the DMA, takes everything to a buffer, and then you have other processes that can access the DMA memory. Instead of extracting the DMA data to another memory section, and then they need to access it. So no, here you can perform it using DMA. I will show it next. But this can improve speed. It can make the development easier, the architecture easier. So I really recommend trying it yourself. Let's see how it works. Okay, let's open the PCI diag code. Okay. So I have this IPC curve alloc and share. Okay, as we see that this is the message that was printed after the memory was allocated. Okay, the buffer was allocated. We can see it here. WDS shared buffer alloc is maybe the most important function in this routine, because it is essentially allocating the shared buffer. And again, you can add the parameters here. The handle is being transferred here. Okay, if we talk about, so this is the size of the buffer that is allocated. As I said, it's predefined. It decides the bit mask, if it's contiguous, non-contiguous, if it's one segment or more, and of course a pointer to the buffer. And you can see here again the prints and other functionalities that can be added here. Okay. Okay. So let's go back and continue with the presentation. As I said, you can do the same thing with the DMA. Okay. If I'll go to my groups, wait a second. Let's say open the device. Okay, I want to allocate or free memory for DMA. Allocate the contiguous memory, say for 10,000. Choose 0 as a default. I can see that I have the allocation done correctly. I have the user address, the physical address, the size, everything looks good. And then I have an option to send the buffer through IPC to all group processes. So let's choose 4. And I can see that I got a DMA buffer in this section. So again, very easy. The code is running in the background. You can add, modify it, add your functionalities, and develop your driver with the complex functionalities with ease, relatively. Okay, I just want to see that I haven't missed anything. Let's go over here to the code. This is freeing the buffer. Okay, so this is important when we're talking about, just a second. We're talking about the functionalities, okay? About what are the data supposed to transfer, okay? What is the type of the data that is being transferred? So here you need to add your own functionality, if you added functionality. So in this case, if I choose 1, it is go to menu SB alloc config, okay? Which is expecting to receive a specific value, okay? A specific value. So you need to add your functionalities here in this section. I think we went through the more important functions in here. Okay. So this webinar was the first one about IPC and covering the 16.3. We have previous webinars. Okay, they were all uploaded and added to YouTube and to our video section on our website. We had webinars about predefined action flow, DMA, debugging, as I said, interrupt handler and IPC, predefined action, test sign mode. We will add this video to our library. So I recommend going over and watching it. We have blog posts on our website on different matters and subjects. And we have the WinDriver Academy, which includes short videos about specific functionalities of WinDriver, performing DMA, overviewing USB and PCI, driver distribution, INF mechanism, and more and more. So I recommend visiting our academy under WinDriver's website and learn. Maybe there are a lot of things in WinDriver that are not known, and some functionalities are not being used, and you may benefit from it. So again, like IPC, discover more WinDriver functionalities. It can make your driver faster, the development process more pleasant and enhanced. So thanks again for everyone who listened. If you have any questions, feedbacks, anything, feel free to contact me here, Daniel B. at Django, and I'll be happy to help. Thank you.